Today is June 9th, 2022. Today I will talk about a measurement method which I developed in 2020. The method allows a high-precision measurement of anisotropy field, coefficient of spin-orbit interaction, internal magnetic field in nanomagnet, and a magnetic field created by a spin accumulation in nanomagnet. It is one of three high-precision measurement methods which I have developed. Another two are measurement of spin polarization and measurement of coercive field. In case you are working with a nanomagnet, I highly recommend you to use them. You can find a detailed description how to use it in my website here. I will show you how to do measurement, how to process measurement data, and how to evaluate each parameter. You can use either my raw measurement data, which you can download, or your own data. I will describe how to use the measurement data to improve the efficiency of the magnetization reversal, either by electrical current or by gate voltage, for memory application or for sensor application. I will explain the details of magnetization reversal mechanism using the classical mechanics based on Landau-Lifshitz equations and using quantum mechanics. I will explain the quantum mechanical meaning of the spin torque and the spin precession. I will explain the reasons why the newly introduced field-like torque severely violates laws of quantum mechanics. I will explain about the interpretation problems and possible systematic errors of popular measurement techniques, which are called the second harmonic measurement and the zero harmonic measurement. I will give some technological recommendations on how to improve the fabrication of nanomagnet, which are based on my personal experience. The explanation consists of several videos, each of which are about specific aspects of the measurement and data interpretation. If you are only interested in specific part of this topic, please watch a specific video which explains that specific part. Below this video, you can find the link to a specific video part. Next, I will give a short overview of each video part. In the video number 1, I will briefly talk about the properties of spin-orbit interaction. I will explain about the relativistic origin of spin-orbit interaction and how the electrical field of atomic nucleus may create a rather strong magnetic field of spin-orbit interaction. Next, I will talk about the rules of breaking the time inverse symmetry and the reason why an external magnetic field enhances spin-orbit interaction. Next, I will talk about this linear relation between external magnetic field and magnetic field of spin-orbit interaction, and about the symmetry and physics arguments which are behind this important linear relation. Next, I will talk about relation between an orbital deformation and the strength of spin-orbit interaction. In the last part, I will explain how the deformation of orbital at the interface creates a perpendicular magnetic anisotropy in nanomagnet. In particular, how the magnetic field of spin-orbit interaction at the top layer changes equilibrium magnetization direction from in-plane to perpendicular to plane. In video number 1C, I will talk about the internal magnetic field in nanomagnet. I will explain the difference between global, local, and average magnetic fields. Next, I will explain the individual nature of magnetic field of spin-orbit interaction. Next, I will describe how to measure experimentally internal magnetic field in nanomagnet. Finally, I will analyze experimental measurement of internal magnetic field in iron-boron nanomagnets. In video number 2, I will talk about the measurements method of spin-orbit interaction and perpendicular magnetic anisotropy. I will start by discussing how, in principle, it is possible to measure the strength of spin-orbit interaction and the strength of perpendicular magnetic anisotropy. I will explain the reason what holds the magnetization along the easy magnetic axis and how to measure the strength of the holding force. Next, I will describe the experimental setup and main idea behind the proposed measurement. Next, I will discuss the main mathematical expression on which this measurement is based. In video number 3, I will explain the first step of data analysis of how to evaluate the anisotropy field and offset field from raw measurement data. I will show how to download and analyze program and measurement data from my website, how to check measured properties of nanomagnet, which I already have fabricated. I will explain about format of measurement data. Next, I will explain mass, which is used for evaluation of anisotropy field from the raw measurement data. I will explain the problems and systematic errors which exist for this procedure. Next, I will show how to remove the systematic errors. In the last part, I will explain how to evaluate the magnetic field which is created by spin accumulation or offset field in short. In video number 4a, I will explain how to calculate anisotropy field and offset field from the raw measurement data and how to do automatic fitting using my first program. I will explain all specifics of the program operation, data format, and how to check the flow of the automatic fitting procedure. In video number 4b, I will explain the observed dependence of coefficient of spin-orbit interaction on the direction of the applied external magnetic field with respect to the film surface. A clear peak was experimentally observed, which correspond to the direction of orbital deformation of top atom at interface. I will explain the reason why this observed peak is related to the features of orbital deformation at the interface. In video 5a, I will analyze the measurement of anisotropy field. First, I will explain how to evaluate coefficient of spin-orbit interaction. I will explain the reason why the spin-orbit interaction misaligns the spin from the direction of external magnetic field and how the strength and polarity of spin-orbit interaction can be evaluated from it. Next, I will explain why coefficient spin-orbit interaction is large in multilayer nanomagnet and small in single-layer nanomagnet. Next, I will explain about measurements of oscillation of anisotropy field and why this oscillation is an important characteristic of nanomagnet. Next, I will explain why the spin-orbit interaction depends on polarity of magnetic field and how to measure it. In video number 5b, I will analyze the relation between anisotropy field and coefficient of spin-orbit interaction. I will explain the reason why there is a linear dependence between anisotropy field and coefficient of spin-orbit interaction. I will discuss the reasons why the slope of this dependence is positive for single-layer nanomagnet but negative for multilayer nanomagnet, and why this slope is important characteristics of fabrication technology of nanomagnet. I will explain the dependence of coefficient of spin-orbit interaction on thickness and interface quality. I will explain influence of demagnetization field on anisotropy field and why does it depend on the interface quality. In video number 6, I will analyze the origin and properties of magnetic field created by spin accumulation or offset field in short. I will discuss about its typical measured value and basic properties in iron-boron nanomagnet. I will explain dependence of offset field on the strength of the spin-orbit interaction. I will explain the reason why offset field is larger in multilayer nanomagnet and smaller in single-layer nanomagnet. I will discuss whether offset field has one or two independent components. I will explain the interesting dependency of direction and magnitude of offset field on the external magnetic field. In video number 7, I will analyze dependency of anisotropy field and offset field on electrical current or sort effect and on gate voltage or VCMA effect. First, I will explain the reason why the spin accumulation makes anisotropy field and offset field dependent on the electrical current. Next, I will explain the experimental data of current dependency of anisotropy field. Next, I will explain the linear and square contribution of current to anisotropy field and which contribution is important for the parametric magnetization reversal. I will explain about the thermal contribution and contribution due to the spin accumulation to the current square dependency of anisotropy field and how to distinguish between them. Next, I will explain the experimental data of current dependency of offset field. At the end of this video, I will explain the experimental data of gate voltage dependency of anisotropy field. Video number 8a, I will talk about magnetization reversal by electrical current or by gate voltage. In particular, about merits of parametric resonance for effective magnetization reversal. First, I will discuss the possibilities of magnetization reversal utilizing the measured effect of current modulation of anisotropy field and offset field. Next, I will compare two mechanisms of current-induced magnetization reversal, which are the spin transfer torque and parametric reversal. Next, I will explain the quantum mechanical description of the process of magnetization reversal, using as example a mechanism of spin transfer torque. I will discuss several interesting predictions of quantum mechanical description of magnetization reversal, such as reduction of precession frequency and the reduction of the precession damping due to the spin injection. At the end of this video, I will explain why the parametric mechanism of magnetization reversal is much more efficient than spin transfer torque mechanism. In video number 8b, I will explain about the effective parametric magnetization reversal using measured effects of the modulation of anisotropy field and offset field by the electrical current or by the gate voltage. First, I will discuss requirements for parametric reversal and how the measured current modulation of anisotropy field and offset field matches those requirements. Next, I will discuss the difference between efficient and inefficient parametric resonance and the importance of the positive feedback loop, which makes the parametric resonance to be efficient. Next, I will discuss several examples of inefficient parametric resonance. As a first example, I will explain why it is impossible to reverse magnetization during the conventional fMR measurement. Next example of inefficient parametric resonance is the microwave-assisted hard disk recording. After that, I will describe the required condition for parametric magnetization reversal using current modulation of anisotropy field or using current modulation of offset field. At the end of the video, I will explain about parametric magnetization reversal using a gate voltage. In video number 9a, I will talk about misinterpretation of so-called second harmonic measurement, an incorrect introduction based on this measurement of two torques, the damp-like torque and field-like torque. I will start with explanation of the details of the second harmonic measurement. I will show that there are many contributions from different effects to this measurement. I will explain difficulties for correct interpretation of this measurement because of a large number of different contributions. Next, I will explain symmetry reasons why the two torques, the damp-like torque and field-like torque, were introduced for the explanation of the measurement of second harmonic. Next, I will show the direct measurement, which details I have explained in previous video, does not support the existence of the two different torques. At the end of this video, I will explain another measurement method, which is called the zero harmonic measurement. This method is very similar to second harmonic measurement and has similar problems. In video number 9b, I will compare two descriptions of the spin dynamic. The first description is based on classical mechanics and Landau-Lifshitz equations. The second description is quantum mechanical. I will describe which quantum effect is described by each part of Landau-Lifshitz equations. First, I will show that the first precession term of Landau-Lifshitz equations describes the broken time inverse symmetry. I will show that the spin precession angle is directly proportional to the percentage of electron filling of spin up and spin down energy levels. Next, I will show that second term of Landau-Lifshitz equations describe transition between spin up and spin down energy levels. Even so, the classical Landau-Lifshitz equation describes spin dynamics rather well and well matched to the quantum mechanical description. There are cases when the Landau-Lifshitz equations hits its limits. I will describe how to correct these cases. Next, I will describe the newly introduced field-like torque and the reason why it severely violates laws of quantum mechanics. In video number 10a, I will describe how to use the data measured by described method in order to evaluate the problems and imperfections on fabrication technology. I will explain how the fabrication technology can be evaluated from three dependencies: anisotropy field, amplitude of oscillation of anisotropy field, and internal magnetic field as a function of coefficient of spin-orbit interaction. Next, I will explain about the critical thickness, at which the direction of equilibrium magnetization changes from perpendicular to plane to in plane. I will explain the reason why the critical thickness exists and why the critical thickness is strongly influenced by interface quality. I will explain how magnetic field of spin-orbit interaction and demagnetization field influence the critical thickness. In video number 10b, I will describe how to use the measured data to optimize the fabrication technology of nanomagnet. I will give 7 technological recommendations on how to fabricate a high-quality interface, and therefore on how to improve the performance of nanomagnet. Next, I will discuss possible technological optimizations to improve the efficiency of the spin transfer magnetization reversal. Next, I will discuss possible technological optimization to improve the parametric reversal. If you are interested to see the content and other parts of this video, you can find the links below this video.